Hi everyone. So in this video, we're going to continue to talk about the graphs of sine and cosine. So specifically, we're going to be focusing on some different properties of these functions. We're going to talk about their domain and range. We're going to talk about something called periodic functions, and we'll see that sine and cosine are both periodic functions. And then we're going to talk about even and odd functions, and we'll determine whether sine and cosine are even, odd, or neither functions. But before we get to that, I just want to kind of review what the general shapes of these graphs look like. So the graphs of f of t is equal to sine of t and g of t is equal to cosine of t. So I mentioned this a little bit last time, but in our last video, when we plotted or when we graphed these functions, we plotted a lot of points. And it would have taken a really long time to calculate all of those points and put them all together. We did it once, or at least kind of did part of it together once, so you could really kind of see exactly where that shape of the graph is coming from. But you're not going to want to do that every time. So I want you to eventually have the general shapes of sine of t and cosine of t. I want you to be really familiar with them to the point where you could sketch their shape really quickly in the same way that you might be able to do for like f of x is equal to x squared. That's a graph where you don't have to plot a gajillion points. You just maybe plot a couple and then you kind of fill in what you know the shape is. So similarly for these two graphs, I think that if you can focus on a few specific t values that are very easy to calculate sine and cosine for, that will give you kind of the skeleton of what the shape of the graph looks like. And then as long as you're familiar with the rough shape of the rest of it, you can just kind of fill it in. So I recommend pausing the video, determining sine and cosine of these, I guess it's 5 angles I'm suggesting, and then use those to sketch the two graphs. Okay, so first thing I want to do is just go to those 5 different angles and put down the terminal points so that we can then just refer to them as we sketch our graphs. So first angle was t is equal to 0. The terminal point there is 1, 0. Then we have t is equal to pi over 2, so that would be this angle here. Terminal point for this angle is 0, 1. Then we have pi, so at an angle of pi, the terminal point is negative 1, 0. And then finally we have 3 pi over 2, and so 3 pi over 2, the terminal point is 0, negative 1. And I guess I should also say 2 pi, well, that's coterminal with 0, so that's the same terminal point that we had at 0, right? So let's start with sine of t. So for sine, we're just evaluating. So the way this function works, remember, is that you're plugging in angles. Those are your inputs. Those are your horizontal coordinates of your points. And then the outputs are going to be just sine of each of those angles. And so the unit circle is what's used to actually calculate what sine of those angles are. But once you have the value of sine, then you're plotting that as the vertical coordinate on your graph. So for example, if we're going to an input of 0, so it's an angle of 0, we can see that sine of 0 is 0. So maybe I'll write that down. F of 0 is equal to sine of 0 is equal to 0. And so we know that our graph goes through the point 0, 0. Then if we go to pi over 2, f of pi over 2 is sine of pi over 2, which is the y-coordinate of the terminal point at pi over 2, which is 1. And so that tells us that when our input is pi over 2, our output should be 1. And so I'm going to plot the point pi over 2, 1. Then we have f of pi. So when we're at an angle of pi, the y-coordinate is 0. And so that tells us that sine of pi is equal to 0. And so that means that when our input, when our horizontal coordinate is is pi, the y-coordinate should be 0. Then we have f of 3 pi over 2. So sine of 3 pi over 2. That's the y-coordinate at an angle of 3 pi over 2, so that's negative 1. And so that tells us that when our input is 3 pi over 2, our output should be negative 1. And then finally, f of 2 pi, well, that's going to be the same as, so sine of 2 pi is going to be the same as sine of 0, right? Because they're coterminal, so that is also 0. So those are basically the 5 points that you want to be able to know exactly where they are on your sine graph. And then between there, you just want to make sure that you're kind of filling it in like a curved way. And I guess one other point that you might want to know is that when you go through pi over 6, that should be a height of 1/2. That can kind of help you guide what the curve looks like. But honestly, for most purposes, you're not going to need to be perfect. You're just going to want to know what the general shape looks like. And so it's usually enough to get just these 5 points down and kind of fill it in between. One thing that I see students do incorrectly a lot is for some reason they'll draw it kind of like this, like just like make everything straight lines. And that's just not what it looks like. You know, we graphed this last time. We saw that it has kind of a curve to it. So make sure, you know, I'm going to be in general with graphing these, I'm not looking for things to be absolutely perfect, but make sure you at least show that kind of general curved shape. Okay, so now we can do cosine, same idea, right? We just want to graph those key 5 points. So g of 0 would be cosine of 0. So looking at the terminal point at 0, we can see that cosine of 0 is 1. So that means that our graph should go through the point 0, 1. G of pi over 2, so cosine of pi over 2, that is equal to 0, looking at our terminal point on the unit circle, so we should put a point at pi over 2, comma 0. G of pi, so it's cosine of pi. So we're looking for the x-coordinate of the terminal point at an angle of pi, and that's -1. And so our graph should go through pi, -1, so that's down here. G of 3 pi over 2, so that's cosine of 3 pi over 2. So the x-coordinate at that terminal point is 0, and so we know that our graph should go through 3 pi over 2, 0. And then finally, g of 2 pi, so that's cosine of 2 pi. That's the same as cosine of 0, so that's also 1. So at 2 pi, we're back up at 1. And then I think for some reason people have a little bit more trouble sketching this graph. I think actually with cosine, that's where I more often see people just draw like a V or something like that. Remember, it still has the same curvature. Like it really is the same exact shape as sine, just kind of a different part of the curve. So you know, just try to make sure that you draw some kind of a curvature to it. So it's more like this and this. It's not like, doesn't have to have like a whole lot of curve, but it should have some curve to it. Okay, so those are our two basic graphs, and that's just between 0 and 2 pi. And I guess I should have added that here. So we're specifically sketching the graphs of sine of t and cosine of t on the interval from 0 to 2 pi, or maybe I'll say it like this, for t between 0 and 2 pi, because I want to make sure I make that distinction. These are not the entire graphs of sine and cosine. They're just kind of a little snippet that is representative. Okay, so I want to start getting into some of these different properties that I mentioned. So the first one I want to talk about is domain and range. So first thing I want to do is just quickly remind you what domain and range are. So recall that the domain of a function is the set of all inputs. So all of the numbers that you are able to plug into that function is called the domain of the function. And then similarly, the range of a function is the set of all outputs of your function. So all of the possible numbers that could come out. So I want to just verify what the domain and range are for these two functions. And I want to think about them both kind of graphically, because you know, now that we know what the graphs are, we can use that to figure out the domain and range. But I also want to think in terms of how sine and cosine actually work as functions, why that kind of aligns with what we can see the domain and range are from the graph. Okay, so what is the domain? So if you're looking at the graph, and so by the way, we'll see that sine and cosine have the same domain and range, so we can kind of just look at both of their graphs together to determine these things. So the domain, if you're looking at the graph, you're basically looking at what are all of the, in this case, T values that are included in the graph. And so remember, these graphs keep going, right? I kind of chose an arbitrary place to cut them off, but they keep going and going and going. I showed you in Desmos, they literally go on forever in both directions. And so what that tells us is that the domain is going to be all real numbers. So the domain extends infinitely in both directions. So the way that we write all real numbers in interval notation is negative infinity to infinity, and we put parentheses. And the reason that this is the domain is because you can take sine and cosine of any number. And I'll say it as of any angle, but really like any number you pick out, you can interpret it as a number in or an angle in radians and take sine and cosine of it. So sine and cosine of any angle. So like, pick a random number, let's say 1,274. You could interpret that as an angle in radians and take sine and cosine of it. I don't know off the top of my head what the values would be, but if you type that into a calculator, it will tell you exactly what sine and cosine are of that angle. So truly any number you can take sine and cosine of. We'll later on be talking about the graph or the graphs of some other trig functions. So for example, tangent, and then all the reciprocal trig functions. And if you recall with those, there were some angles that caused issues, right? Those ones became undefined when we plugged in certain angles. And so those ones, the domain is not going to be all real numbers, but with sine and cosine, you can plug in any angle you want. Okay, so what about the range? Well, the range we're looking at vertically, what are all of the values that are included in the graph? And so we can see from the graph that the minimum value that sine and cosine ever reach is -1, and the maximum value is +1. So I'm going to kind of denote that in our graph here. And then I want to also talk about how we could understand that even without looking at the graph. So the range is going to go from -1 to +1. And so in interval notation, that would look like this. We're putting a bracket because -1 and +1 are included, right? We know that the graph actually touches positive and -1. So why would that be the range? Like, why is it that sine and cosine never exceed 1 or never are less than -1? Maybe pause the video and think about that for a second. Like, think about the way that we evaluate sine and cosine and why that could kind of show that sine and cosine cannot ever exceed 1 or be less than -1. So it really has to do with the unit circle, right? So the way that we are evaluating sine and cosine is by looking at x and y coordinates on the unit circle. And remember that the definition of the unit circle is that it's a circle with a radius of 1, right? And so if it has a radius of 1, how could you ever have an x or y coordinate on the unit circle that is bigger than 1, right? Like the very biggest x and y values you're going to get are going to be at these 4 points, right? So we have 1, 0, 0, 1, -1, 0, and 0, -1. And all of the other points between those, they're never going to have an x or y coordinate that is bigger than 1 or smaller than -1. So we can say that the range is -1 to 1 because sine and cosine are determined by points on the unit circle. And basically points on the unit circle can never have coordinates that are bigger than 1 or smaller than -1. And points on the unit circle can never have coordinates. I'm just going to say coordinates. I mean either x or y coordinates greater than 1 or less than -1. And then additionally, notice that because of the circle kind of continuously going through all of the different values between these 4 points I highlighted. That's why the range includes all y values between -1 and 1, right? Like we're really like, as you go around, you're really gonna go through all of the different x and y coordinates that are between -1 and 1. And so the range includes all of those values. All right, so that is the domain and range. Next thing I want to talk about in terms of these functions is something called periodic functions. So I first want to define what a periodic function is, and then we'll talk about how sine and cosine are related to this concept. So a periodic function is a function that repeats its values on regular intervals. So basically that just means that, you know, you have all these different y values that the function is going through, and it's kind of going through them, and then it's cycling back through those same y values, and then it's cycling back through them. And it's doing that on regular intervals, meaning that if you look at how many different horizontal coordinates it goes through as it goes through those different values, that same amount of horizontal coordinates is the same amount of time it takes to go through that pattern again. And this will become, I think, clearer once we look again at what the graphs of sine and cosine look like, because they're basically like the most important examples out there of periodic functions. So periodic functions have something called a period. So the period of a periodic function is the length of one cycle. And so I think when we look at an example, you'll see what I mean by cycle. But basically think of the cycle as, you know, going through all of the different y values, but before it kind of repeats the pattern. So before repeating the pattern. Okay, so an example, and actually like the, again, most important example of a periodic function is sine and cosine. So f of t is equal to sine of t, and g of t is equal to cosine of t are both periodic functions. And so maybe pause for a second and ask yourself, you know, what is the period of sine and cosine? So what is the length of one cycle? How many different t values does it go through before the pattern starts to repeat itself? So it's 2 pi, right? And we saw this in the last video. If you sketch the portion of one of these graphs from 0 to 2 pi, you're really kind of capturing the entire shape of the graph, because it goes through that entire shape again, and it does that over another 2 pi, and it keeps doing it over and over. So they're periodic functions with a period, or I'll say with periods of 2 pi. So how we can see this is if we look at the graph, if you look at one cycle, so we see that one cycle happens from 0 to 2 pi. Let me draw that a little better. So that is a length of 2 pi, right? From 0 to 2 pi, if you were to subtract 2 pi minus 0, that would give you a distance of 2 pi. And then we see the same thing happening again from 2 pi to 4 pi. Right, from 2 pi to 4 pi, that is also a distance of 2 pi. And so you would see another pattern repeating, or the same pattern repeating itself again from 4 pi to 6 pi. Also from -2 pi to 0, from -4 pi to 2 pi. So the pattern just repeats every 2 pi. And so that's how we can see that that is the period of these functions. So I want to talk a little bit about why these functions have this period, because I think that is really essential to kind of remembering that they have the period. So, you know, one thing that I really try to emphasize in this class, it's gonna eventually feel like maybe there's a lot of different kind of facts to memorize. And I really don't want you to think of it as facts to memorize, because I think a lot of these, if you just understand how the sine and cosine functions work, then you can just kind of understand these facts as just being a part of the function rather than as being like a separate fact that you need to memorize. Okay, so why do they have this period of 2 pi? So I want to look at an example, because I think if we look at an example of evaluating sine and cosine of a couple of different angles, it will really illustrate why the period is 2 pi. So maybe pause the video and do this yourself. Evaluate sine of pi over 6, cosine of pi over 6, sine of 13 pi over 6, and cosine of 13 pi over 6, and see what you get. Okay, so let's start with pi over 6. So pi over 6 would be this angle here. So this is pi over 6. And the coordinates of this point are square root of 3 over 2 and 1/2. And so that tells us that sine of pi over 6 is equal to 1/2, because that's the y coordinate. And then it also tells us that cosine of pi over 6 is equal to square root of 3 over 2. Okay, so what about 13 pi over 6? So 13 pi over 6 is the same thing as 2 pi plus pi over 6, right? Because 13 pi over 6 would be, or 2 pi would be 12 pi over 6. So 12 pi over 6 plus pi over 6 gives you 13 pi over 6. And so what would that angle look like? Well, it would be coterminal with pi over 6, but it would involve an additional rotation. So it would look like this. So it would give you that same terminal point, but it would include, it's not technically the same angle, right? It includes this extra rotation. And so we can see that actually you get the same exact values, right? We find that sine of 13 pi over 6 is equal to 1/2, and cosine of 13 pi over 6 is equal to square root of 3 over 2, because 13 pi over 6 is coterminal with pi over 6. And so this is something we actually talked about, or we've talked about a few times, but I mentioned that for sine and cosine, if you're looking at coterminal angles, the value of sine of 2 different coterminal angles will be equal. The value of cosine of 2 different coterminal angles will also be equal. And so that's exactly what we're seeing here. So what is the connection to the graph and to this idea of it being periodic? Well, let's look at where these points lie on the graph. So sine of pi over 6. So this isn't like, this graph doesn't have all the subdivisions we need, but I can tell you it's here, right? It's like about here. And then cosine of pi over 6, that would correspond to this point. So this point at the bottom, this is the point pi over 6, 1/2. And then this point on the graph of cosine, this would be the point pi over 6, square root of 3 over 2. And then if we go to 13 pi over 6, so again, it's not exactly here, but I'll tell you it's just here. So this is the point 13 pi over 6, and it has the same y coordinate, right? It's 13 pi over 6, 1/2. And then similarly, on the graph of cosine, we have 13 pi over 6, square root of 3 over 2. And so what I'm getting at here is if we compare the locations of these 2 different angles, so if we compare from pi over 6 to 13 pi over 6, what is that length? Like how far is it between those 2 angles? Well, it's 2 pi, right? And what are we seeing happen 2 pi apart? Well, the function's values are repeating itself, right? We're getting the same height happening a distance of 2 pi from one another. And that same thing is going to keep happening, right? If you inch over just a tiny bit and look at another angle, you're going to see that same output happening on, just a little bit past 13 pi over 6. And so because what we're seeing happen here happens for every single angle, it just causes the graph to copy itself, right? All of the different heights that the graph is going through in this first part between 0 and 2 pi, it's going to go through all of those same heights again. So really the fact that The idea of coterminal angles is really the reason that this function is periodic with a period of 2 pi. And I do want to quickly show you just a little bit more of this on the graph here so you can really see. So here we have the point pi over 6 1/2. I'm just going to do it on sine, so let me just get rid of cosine because it's the same idea with cosine. So 13 pi over 6 1/2, we already talked about that. That is pi over 6 plus 2 pi. So what happens if we add 2 pi to 13 pi over 6? Well, that gives us 25 pi over 6. So 25 pi over 6 is 13 pi over 6 plus another 2 pi. And if we look over at the graph at 25 pi over 6, we see that same height again. So again, the graph is repeating itself. And same thing would keep happening if you keep going this way. Similarly, if you subtract 2 pi from pi over 6, you would get negative 11 pi over 6. So that is another angle that is also coterminal with pi over 6, but it's a negative angle. So a negative 11 pi over 6, we also see a height of 1/2. And so we can just see that same repetition happening over and over. And so that is why the graph is periodic. So there are two identities. So we talked a little bit about identities in the past. Identities are just equations that are true for all values of their variables. And I think the place we talked about it before was the Pythagorean identity, right? Cosine squared plus sine squared is equal to 1. So the periodic identities that I'm about to write down are we actually pretty much already talked about these in another video. So I told you in another video that if you have two angles that are coterminal, so let's say theta 1 and theta 2, then sine of theta 1 is going to be equal to sine of theta 2. And cosine of theta 1 is going to be equal to cosine of theta 2. So what I'm about to write down is just a slightly different variation of that. So basically, sine of theta plus 2 pi k is going to be equal to sine of theta, and cosine of theta plus 2 pi k is going to be equal to cosine of theta, and these are true for all angles theta and all integers. So an integer is a whole number, positive or negative, all integers k. So I know this kind of just looks like a whole bunch of variables and whatnot. So let's try to really unpack what this means. So remember that adding 2 pi k, this basically means just adding any multiple of 2 pi. So you can think of this as meaning any multiple of 2 pi. So it could be 1 times 2 pi, it could be negative 3 times 2 pi, it could be 7 times 2 pi, any whole number multiple of 2 pi. And so all that's going on here is that we're saying that if you have an angle and you add on some multiple of 2 pi, that if you then take sine of that result, that it's going to be the same as taking sine of your original angle, and then same thing with cosine. And so this is really just saying, again, that if you have two coterminal angles, that sine of those coterminal angles and cosine of those coterminal angles are going to be equal. Because if you add any multiple of 2 pi, that's just going to give you a coterminal angle. So these, again, are called the periodic identities. Like I said, we really already talked about these, so I don't want you to think of them as some new fact you have to memorize, but it is something that's convenient to remember, that basically adding any multiple of 2 pi to an angle does not change the value of sine or cosine because it's giving you this coterminal angle. Okay, so last thing for this video is I want to talk about even and odd functions. So I want to first refresh your memory on what even and odd functions mean, and then we'll look at sine and cosine and see whether we can determine if they're even or odd. So this is something you should have learned about in your 141 class. So an even function, so I'm going to say it this way. Recall that a function f of x is called even if f of negative x is equal to f of positive x. So basically the way that I would think about this statement is that if you take the same number and plug in a positive and negative version of the same number, you get the same result. And don't worry, we'll look at an example in a moment of an even function and see how that works. A nice thing to know about even functions is that they are symmetric about the y-axis. And let me actually, I'm just going to give myself a tiny bit more space here. I feel like I didn't give myself enough room. And let me actually, I'm just going to make this a different color because I feel like it's going to be, okay. So a function f of x is called even if f of negative x is equal to f of x. And then the other thing to know about even functions, like I said, is that even functions are symmetric about the y-axis. I didn't leave myself enough space again. Okay, so that's even functions. And by the way, what do I mean when I say symmetric about the y-axis? I mean that if you were to reflect the graph over the y-axis, it would still look the same. So here's an example of an even function. F of x is equal to absolute value of x minus 1 is an even function. So let's kind of demonstrate to ourselves that it is in fact an even function. So for example, if we were to evaluate f of negative 1 and f of positive 1, we want to verify that we're getting the same result both ways. So f of negative 1 would be equal to 0. And we can either do that by looking at our graph or just by plugging it into our function, right? Absolute value of negative 1 is 1, minus 1 is 0. F of positive 1 is also 0. Similarly, f of negative 2, if you plug it into the function, absolute value of negative 2 is 2. 2 minus 1 is 1. We can also see that on the graph, right? We have this point here, negative 2, 1. And then f of positive 2, absolute value of 2 minus 1 is also 1. And so what we can see is that we have points, and the same thing would keep happening. I'm not going to do it for 3 and negative 3, but the same pattern is going to happen for any positive and negative version of the same number. And it's basically because you're taking absolute value of it, right? And so it doesn't matter whether that number is positive or negative, you're going to get the same output either way. So these are just some examples of seeing that happen. And then we can also see that this graph is symmetric about the y-axis, right? So f of x is symmetric about the y-axis. Okay, so that's what even functions look like, more or less. So now let's talk about odd functions. So a function f of x is called odd if f of negative x is equal to negative f of x. And so that one I think is a little harder to make sense of. We'll see it in an example in a moment. Basically what I would say is that if you have opposite inputs, you're going to get opposite outputs. So really, like this first one, we can think of this as meaning opposite inputs are going to yield the same output, right? If you plug in opposite, and when I say opposite, I mean like one's positive, one's negative. So opposite inputs yield the same output. We can think of this as meaning opposite inputs yield opposite outputs. So that would mean that if you plugged in, let's say, positive 2 and negative 2, you wouldn't get the same result, but you'd get the exact opposite result, just opposite sign results. And so odd functions, they have kind of a slightly trickier type of symmetry. What they're called is symmetric about the origin. I think it's best to kind of see that by example. So we'll look at an example in a second. But basically, symmetry about the origin means that if you were to reflect it over the y-axis and over the x-axis, that it would return to the original shape. So odd functions kind of have this shape where they're kind of doing the same thing but in opposite directions. With the even functions, they're doing the same shape mirrored over the y-axis. For odd functions, they're taking the same shape, but it's flipped in a different way. It's kind of going opposite directions diagonally from each other. So we can see some examples of how this is an odd function by testing some numbers. So for example, if we were to plug in, so by the way, this is negative x cubed is this function. If we, for example, were to plug in -1 versus +1 and see what our results are, well, if you plug -1 in, you're going to get an answer of +1. And that's because basically, if you take -1 and cube it, sorry, my screen got stuck. If you take -1 and cube it and then apply a negative sign, it becomes +1. Whereas if you plug in +1, that would be cubing +1, then applying a negative sign, so you get -1. And so notice that our results are opposites of each other. One of them is 1, one of them is -1. Similarly, if you plug in -2, so that would be -2 cubed is -8, but then you apply a negative sign, you would get +8. So g of -2 is +8. And then g of +2 is 2 cubed, but then make it negative, so it's -8. And so again, we're getting the opposite results when we plug in opposite inputs. And then additionally, this has this kind of symmetry I was describing. And again, I think it's a little harder to picture, but if you were to take this graph and reflect it over the y-axis and then reflect it over the x-axis, you would get back to the original shape. So this graph is symmetric about the origin. One thing I want to add is that not all functions are either even or odd. So in this video, we're going to be focusing on ones that are either even or odd, but not every function is even or odd. So for example, if you were to take this absolute value graph and just shift it a little bit horizontally, it would no longer be even because it would no longer be symmetric about the y-axis. Or if you were to take the negative x cubed graph and shift it actually anywhere, vertically or horizontally, it would no longer be odd. So not every function is even or odd, but it's a nice way to categorize certain types of functions. Okay, so I want to now talk about whether sine of t and cosine of t are even or odd functions. So we're going to do this by looking at the graphs eventually, but before we get to the graphs, I want to think about this in terms of this idea of comparing your inputs, like what do you get when you plug in opposite inputs? So let's start with looking at sine of t. So what I want to do is figure out what do we get when we plug in positive pi over 3. So that would be evaluating sine of positive pi over 3 versus what do we get when we plug in negative pi over 3. So what happens when we take sine of negative pi over 3? So I'd encourage you to pause the video and use the unit circle to answer this question. So positive pi over 3 would look like this, right? This is an angle of positive pi over 3. And so the coordinates of this point are 1/2 and square root of 3 over 2. And then negative pi over 3, well, that would be this angle down here. So this is negative pi over 3. And so notice that negative pi over 3 has the same x coordinate as positive pi over 3, but it has the opposite y coordinate. So that's going to be kind of key to figuring out whether these functions are even or odd. Okay, so what do we get when we plug in positive pi over 3 into the sine function? Well, sine is the y coordinate of the terminal point, so we get square root of 3 over 2. And then for negative pi over 3, we have negative square root of 3 over 2. And so notice that these are opposite outputs. So we plugged in opposite inputs and we got opposite outputs. And this isn't anything special about the angle pi over 3. If you think about it, the same thing would happen for any angle, right? So if I were to just pick some random angle, let's say this was my angle theta, and then if I were to go to the negative of that angle, negative theta, whatever y coordinate I had for positive theta, the y coordinate for negative theta would be the opposite. So it's always going to be true that when you plug in opposite angles, angles with opposite signs into the sine function, you're always going to get opposite outputs. And so we'll see that sine is an odd function. Opposite inputs give us opposite outputs. On the other hand, and let me erase this because it will get confusing now with my color coding. Oops. Okay, so on the other hand, if we now look at cosine, so what happens with cosine of positive and negative of the same angle? So that would be g of pi over 3. So cosine of pi over 3 is the x-coordinate, that is 1/2. And then g of negative pi over 3, again, we're looking at the x-coordinate. But if you compare the x-coordinate of positive and negative pi over 3, they have the same x-coordinate, right? So it's still going to be 1/2. And so with cosine, we plugged in this or opposite inputs and we got the same output. And again, that exact same thing is going to happen for any angle you choose because, and maybe let me just use a totally different color to really emphasize this. If you go to any angle theta on the unit circle, so let's just say this is some angle theta, and you have some x coordinate and y coordinate, and the x coordinate tells you cosine, the y coordinate tells you sine. If you go to negative of that angle, so I'm just going to draw this as exactly negative of the same angle, so that would be negative theta. Notice that the x coordinate of these 2 points is exactly the same. So it's going to have the same x coordinate, but it's going to have opposite y coordinates because the y coordinates are kind of reflected over the x axis. And so the pattern we saw here is always going to be the case. So it's always going to be the case, and I guess I wrote these in the opposite direction than I usually do, but that's okay. So g of t is equal to cosine of t is an even function. And so we can see that it has symmetry about the y-axis. So this is not like the typical kind of view of cosine. So in the past, when we've graphed cosine, we've graphed this part of it that I'm tracing over here, right? So that's from 0 to 2 pi, but that's not the whole graph. So in order to get an idea of whether it's even or odd, we really need to kind of zoom out and look at the big picture, and we can see that it is symmetric about the y-axis. And then sine, on the other hand, so f of t is equal to sine of t, we saw that when we plugged in opposite inputs, we got opposite outputs. So that means that this is an odd function. And again, we can see this kind of, sometimes I like to describe odd symmetry as like a pinwheel kind of shape, right? We're seeing the same kind of shape happen in both directions, but kind of going opposite from each other diagonally. And so that means that it has this type of symmetry called symmetry about the origin. So cosine is an even and sine is an odd function. Maybe I'll put boxes around those because those are important facts to know. But again, it's really not something you have to memorize. If you know what it means for a function to be even or odd, which is something that you should have learned in your previous class, then you can just think about what the graphs look like or go, think of this picture and what happens when you plug in opposite angles, and that should be able to kind of remind you which one is even or odd. So last thing I just want to mention in this video is that sometimes people refer to what are called the even and odd identities. Again, this is just going to be another way of writing something that we've now said a few times. But basically, because cosine is even, we can say that cosine of negative theta is equal to cosine of positive theta, right? Because for an even function, that means that plugging in opposite inputs gives you the same output. So cosine of negative of an angle is going to be the same as cosine of the positive of that angle. And then for sine, well, because sine is an odd function, when you plug in the negative of an angle, you don't get the same result as plugging in the positive, you get the opposite. So sine of negative theta is going to be equal to negative sine of theta. So these are the even and odd identities. And we'll come back to these. Like I said, we're going to do a whole section about identities. And so a lot of these are going to come up again. But here you can actually see why this identity is true and how it's related to the graphs of the functions. All right, so that is it for this video. In our next video, we're going to get into transformations of the graphs of sine and cosine. So I'll see you then.